I'm Branden, a PhD student at University of Michigan, and I'm presenting sort of an oddball from this session. Still traffic infrastructure, but physical traffic infrastructure, vehicles, traffic lights. This was collaborative work with Bill, Alan, Jonathan, and Alex at University of Michigan. So traffic lights. They're ubiquitous critical infrastructure. They're so commonplace that they're essentially invisible to us at this point. Every day we drive down the street and we pass by dozens of traffic controller boxes on the side of the road and we never notice them at all. Every time the light's green, we know it's safe, we drive through without a second thought. So we decided to actually investigate this infrastructure, see if it's as secure as it really ought to be for such a critical position that it's in. So a high-level overview of our work. We ended up finding, so we evaluated a existing deployment working with a anonymous road agency. Got to test on their hardware and on their actual deployment. We discovered several vulnerabilities which could allow an attacker to access the system and actually to influence the controller, change the state of lights. And we really want to emphasize here that it isn't any one weakness in the system, which is really the problem here. It's all the weaknesses. The entire industry has sort of a failure to secure their systems. So first I'm going to talk about the anatomy of traffic infrastructure, and then I'll go into our security evaluations and our findings, and finally I'll tie it up with some recommendations for both road agencies and vendors going forward, how they can fix their systems. So first, let's talk about vehicle detection. So it turns out most traffic lights nowadays detect when vehicles are there and change their light states based upon that. There's a couple of methods for this. The common one is by inductance. You sense the metal of the vehicle above it. There's wired sensors, as seen in the top right, and there's also wireless sensors. Earlier this summer, work by Ceruto focused on these wireless sensors and spoofing the radio communications from them in order to trick the traffic light controller into believing there were cars or weren't cars. There's, in addition, video detections used pretty commonly at a lot of traffic lights, and there's numerous other systems. And really what happens here is that they combine a lot of these systems together to try to get a better feel of whether there really is a car or not. So going inside that traffic cabinet that you all ignore, so there's the metal box right inside the road, sometimes mounted on the pole. Inside of it, we've got a couple of devices I'd like to point out. First, most important one, traffic controller itself. So nowadays, this is a fully computerized system. It's got a Power PC inside of it. It's running VxWorks. This thing takes in the signals from the various sensors around and has a pre-programmed timing plan, combines these and decides what the state of the lights actually ought to be. This underwent quite a transition. In the last 100 years, it started off, electronic timing circuits, and underwent a transition and became this fully computerized device. So also in the box, we've got some relays for actually controlling the lights. But between the two of these, the traffic controller doesn't directly connect to the relays. There's this malfunction management unit, the MMU. So this is, yeah. So it's also called conflict management unit, but yeah, so it was there from the electronic days. In case anything went wrong with the circuit, this thing is there to take over. So let's talk about this a little more. What this really is an electrical failsafe. So they've got this circuit board, they solder in connections and whitelist states of lights. So they say green light and the left, that's good. Opposing green lights, that's bad, don't do that. And so this will watch the outputs from the controller as they go to the lights, and we'll actually override them if they're incorrect. So the override is blinking red lights, and sometimes blinking yellow on the thoroughfare. And so when this device activates, it is a real hardware failsafe. Somebody has to drive out there, open up the box, and press a button to reset the lights. It doesn't have a software connection to be reset. Unfortunately, I'm going to go ahead and ruin it for you all right now. This means you can't have four-way green lights. This device is there watching, it's part of the standard, and it stops that kind of thing from happening, which was unfortunate, but good. So I'd also like to emphasize while we're here how sort of rare this is. So these systems started off as hardware and turned into computers, and even though they're software controlled now, it's still mandated that there's hardware to watch over them. This was really a situation where the traffic industry did something right. seen so many times before where, Theric 25 style, software was in charge, and so everybody trusted it. And this is a state where that didn't happen, which is good. What else is at traffic light? Well, second these things became computers, they wanted radios. A lot of traffic intersections nowadays have radios to communicate with other traffic intersections and back to some kind of a central server. This can be for data reporting, so you want to know how many vehicles pass through an intersection a day, how long they're waiting, et cetera. This is also for active control in some situations, coordination between multiple traffic lights or control from some kind of a centralized location. In addition, they end up putting a lot of cameras on there. Well, we've already got radios, we might as well have a camera, and then we don't have to drive out there and see what's going on. We can just turn the camera on and take a look. All right, so that is what's at a traffic intersection. Let's talk about our specific deployment. So again, we worked with an anonymous road agency. They were willing to support us, give us a lot of information, access to their hardware, access to the deployment itself. But the condition was that they remain anonymous and their vendors remain anonymous, which we agreed to for access to their system. So they're located in an urban area, about 100 lights total in the infrastructure. So they use radio systems. They've got a network set up. So every light is in a tree. They beacon back to the lights before them, so on down the chain, and then finally at the end they've got a 11 gigahertz jump back to a central server. And this is for data reporting only. They don't have any kind of active control on these systems. They just want to be able to read the data from them. There are also two types of radios used in this deployment. 5.8 gigahertz radios are preferred, and they're used in the majority of places. They've also got 900 megahertz radios for times when things like buildings, trees, bridges get in the way of their signal. If they don't have line of sight, they end up using the 900 megahertz. And to give a feel for what these radios are actually like, so these are 20 dBm radios. They're broadcasting about a mile down the road, directional. So they're pretty strong. So first, we took a look at the 900 megahertz radios, and unsurprisingly, ended up finding no encryption enabled on the connections. They relied on a proprietary protocol, and that was basically the only safety they had, frequency hopping. WPA is possible. It's in the settings. You could turn it on, but it's not enabled by default, and in the deployment, they never activated that. The system has a default username and password, so log on to it whenever you want if you look it up online. And then vendor configuration software. So the vendor of this radio provides software to be used to change its configuration. And this expects that you use the original default username and password. And if you change that password, the software no longer works. So let's take a look at the 5.8 gigahertz radios. These are, again, a proprietary protocol. This time it's really similar to AO2.11. So this screen cap at the bottom is when we sat down at a bench on the side of the road. We pulled up Wi-Fi Explorer on Mac, and lo and behold, the traffic light networks appeared. We could see them on our laptop. We couldn't connect to them. Mac just gave a generic error, cannot connect, but we could see them. So when we investigated the hardware itself, we found, again, no encryption. This time it's possible to turn on all the way up to WPA2, but it wasn't enabled again. Again, default username and password. And this time the vendor did a little bit better. The software allows you to change the password, but it still expects one common password throughout all radios in the system. So now that we know these things about the radios, what do we have to do to actually connect to the network? Step one, you need some way to connect to, we decided to attack the 5.8 gigahertz, so you need some way to connect to that wireless connection. You could go ahead and reverse engineer how the protocol works and put a lot of effort in, or you could use a pair of binoculars, figure out what the vendor is, because there's a label on the side, and buy a radio from them. So that approach works pretty well. Then you need some kind of a network name, which, again, you can see on your laptop. So you enter that in, and suddenly you're connected. And now you plug in a laptop over Ethernet to your radio, and you've got full access to the system. And it's important to note here, so this entire system is one private network. If I access the network anywhere, I'm accessed everywhere. I can access all 100 controllers in the system from that one point. Next we decided to look at the traffic controller. So the traffic controller, it's usually physically manipulated. They open up the box. There's a front panel with some buttons, numbers, and menus to walk through. Change the settings that way. There's no access control on this system. It's possible to turn it on, but it is really a second-class citizen. It's very difficult to use, difficult to enable, and they had never enabled it at the deployment we studied. This device also has an FTP server on it so that you can access the database and change settings. In this case, there's a fixed username and password. It's not possible to change them. We talked to the vendor. They confirmed this. Nope, not possible. And so if you're on the network, you can get in that way as well. Looking a little deeper into the controller, we found that it was running a VxWorks operating system. The particular build they're using has a debug port enabled by default. This is so commonly forgotten about that ICS CERT has labeled it as a vulnerability. And in fact, the system was vulnerable to that. You could arbitrarily read and write any memory on the system that you wanted without any kind of access control at all. Actually, it turns out the vendor had already fixed this problem. They didn't list it in any of their change logs. And when the road agency saw that there was an update, they saw that it wasn't important and decided to update their controllers later. Finally, one additional way of accessing the controllers, NTCIP 1202. We get into a bit of an acronym hell trying to define what this stands for, but ITS is Intelligent Traffic Systems. This is a standard by a couple different standards organizations, NEMA, Institute of Transportation Engineers, and others. And this is a standard for traffic system communications. This uses SNMP to manage the controllers and is standard for interfacing with them. It doesn't provide any kind of access control to the system. So in this case, we had it easy. The vendor created another program which allowed you to remotely control these systems through this protocol. It was very easy to sniff with Wireshark. So what we did was we took a look at the kind of packets that were coming from it, and we put together our own library that enabled us to call the commands that were on the front panel of the device to begin with. Then we created sort of a traffic controller shell, and this shell would allow us to walk through the menus and see what the current status was, even run scripts, do things like change the light states, freeze lights in position. So putting it all together, we can access the network. Once we're on the network, it's easy to access the controller, and now we've got the ability to change the lights of the controller. So at this point, what we really wanted to do was go out to the deployment and try these things. So we did. We had some road agency personnel out with us. We went out to a T intersection in the deployment. So this, in this T intersection was a particularly good target because if the MMU activates, it's blinking yellow on the main road, and only the side road goes to blinking red. And the traffic personnel were there with us, so in case it activated, they could go fix things. We also, just for reference, watched the cars and didn't do this while people were driving through the intersection. So what do we need to do this? So we need a 5.8 gigahertz radio, we need a laptop, and we needed some kind of power for the radio. In this case, I drove my car over to a nearby parking lot, we plugged in a power inverter, and started connecting. So the first thing we did was we tried to connect to the network. We could see the network name for the intersection that was about 200 foot away. And so we tried to connect to it, and it turns out these radios are very directional, and we had a hard time. We couldn't get into it. So we looked up the network name for the next network down the road and connected a half mile down that way instead. And that worked just fine. So now we were on the network. We activated our script, logged into the, sorry, not logged in, there's no access control, connected to the controller, and ran it to change lights. So we could watch as the light was green, and we click the button, it'd turn yellow immediately and then go to red. Along this way, while we were trying things, we actually accidentally triggered the MMU on 2 separate occasions. So if you're wondering whether it's there and working, yeah, it's paying attention. So yeah. Let's take a step back for a second. So what can an attacker really do with this kind of access to the controller? We discovered sort of 3 categories that we're going to place this in. The first is denial of service. So this MMU, it's a powerful thing. It's providing safety for the system. But on the other hand, it's not providing any kind of security. The second we get into the system, it's trivially easy to activate the MMU and get to take over. and then somebody has to physically drive out there to reset it. In this case, it's so much easier for us to activate the MMU than it is for them to drive out there across the 100 installations. Second method, you could use this for traffic congestion. There have been numerous studies. The city of Boston thought they could save over $1 million a year just by reconfiguring the traffic lights to work better. Well, we could cost them $1 million a year by reconfiguring the traffic lights to work worse. Finally, you can actually use this to individually control lights. Video game style, movie style, turn the lights green right as you're going through, turn them red after you. So a couple of recommendations we need to get into here. For the road agencies, follow basic security practices. That's it. For vendors, you really need to enforce security. These kinds of things, when they're not enabled by default, these road agencies aren't turning them on, ever. And so they plug in, they go, security was either there or it's good enough without it. So these kind of things need to be enabled and enforced, especially passwords. You should expect people to change their passwords and really try to prompt them to change their passwords whenever possible. Finally, somebody really needs to be thinking about security. So we contacted the vendor for the controller to tell them about what we'd found, and their response was that they followed the industry standard, and it was the standard that didn't have any security. And so, we did the best we can. So road agencies, the vendors, the standards organizations, they all need to work together to ensure that there's security in these kinds of systems. They're too important to just ignore. Especially as we look forward to the future, if we want to install V2V, V2I installations, we can't even keep our simple networks secure. How are we going to keep these more complex networks safe from attacks? A couple of concluding remarks. So the real problem here that as we see it, is sort of a lack of security consciousness throughout the entire industry. It isn't one vulnerability. It isn't one road agency's problem. It's a lack of everybody thinking about it. These traffic lights underwent this phase change. They started off as electric systems, they went to computer systems, and finally networked computer systems. And along the way, security just didn't keep up. And ensuring that security is in these systems really is important. Thank you very much for your time. With that, I'll take any questions that you've got.
So, Warren Kamari. You say that the MMU stops me from having 4 green lights. Mm-hmm. Can you get around that by just making one direction green, then the other direction green, and doing that fast enough that
we tried that.
Okay.
We were very excited about that idea, but it turns out that the MMU is watching an additional thing, not just the directions of lights, but actually timing of them. So if you go from green to off or green to red without a corresponding yellow in between it, it takes over. Yeah.
Luke Desitels, North Carolina State University. Similar question about the MMU. Mm-hmm. It looked really simple when you showed the image of it.
Yeah.
Is there anything stopping me from making my own at home and installing it at 3 a.m. and then being able to do the 4 green lights once I've changed the hardware?
But if you've got physical access to the system, you can do a lot more than that. Like you can just unplug it, right?
It seems really trivial to get physical access because those boxes are all out there unprotected.
Sure. In this case, physical access involves breaking into a locked box in view of the road, in view of cameras. It's certainly harder than using a radio from a mile away. But if you do break into the box, yeah, you've got full control over the system, definitely.
Anybody? Okay, go ahead.
After that, yeah, we thought about such a thing. It's a little clumsy to attach a radio to the phone, and I never reverse engineered the protocol, so not yet.
Likely a box with cells,
yeah.
Like bars, actual prison crank.
Anybody?
So you're dealing in a world of Gresham's law. How are you going to get any improvement when there's no economic incentive?
That's a good question. The best we could hope for with this individual deployment was that these guys now know what the problems are, and we gave them a list of, like, here's some simple steps you can take to fix it, or at least improve security by a significant amount. For the system as a whole, we're just sort of hoping that bringing attention to it might prompt them to actually start thinking about these things in the standards organizations.
The second question related to possible solutions. Do you know of any other countries that are significantly better or worse about this type of security?
No, I actually don't know of the differences between other countries. We only studied the United States.
I know you can't reveal a vendor. Can you reveal a location of these tests? And are these equipment actually widespread in the US?
Yeah, so we did look into that. So the controller themselves run on, I think, over 100,000 lights in the United States is what the vendor suggests. So it's a significant number.
Okay.
But again, we don't think it's a problem with just this vendor. We think other vendors are going to end up being just as vulnerable in similar or different ways.
Last question.
So, Warren Kamari again. Does this hardware ever show up on eBay? And can I buy some?
Yes.
Ooh, how much is it, roughly? Wild guess.
It varies by a lot, and depending on how old it is. Many of these controllers, they sit around and they're used for 10, 20 years, and then they get sold on eBay for cheap because they're not really worth anything to normal people.
Excellent. Great delivery, Branden. Thanks a lot.
Thank you.
Thanks, Branden, one more time.